Hi again, this is another video on blockchain security, episode 5 this time, and it's all about protocol level security concerns. So if you remember back in the overview video, the first one I did, I said that we are usually secure at the protocol level and there are no issues, cryptographically speaking, and at the protocol level. And of course that's not entirely true. There have been a number of incidents at the protocol level, and if you are into blockchain protocol engineering, it's very easy to get things wrong, and not all blockchains are secure. So in this video, I'll look at some of these issues that can happen at the actual blockchain level. So let's first look at theoretical attacks, which some of these are not that theoretical, as that they are happening all the time. The first and most well-known one is obviously a 51% attack on a proof-of-work blockchain such as Bitcoin and Ethereum, and this is just someone obtaining more than 50% of the computing power of the network, and that way can control the network and reorganize the chain and force their own version of history onto the blockchain. And this has become surprisingly easy on smaller chains because hash power can actually be rented on an hourly basis, and if you do the sums and then work out the numbers, it can actually be quite profitable because you can earn much more double spending quickly than renting enough computing power on an hourly basis to do such an attack. So it's profitable. There's also selfish mining, which is a way of miners increasing their share in the payouts and in the creation of blocks. That basically consists in a group of miners, mining pool, for example, not publishing the blocks they find for a while, immediately start mining the next block without having published to the whole blockchain, and then occasionally they do release their version of the chain, and if they time this right, they can actually increase their share of blocks created and convince other miners that they are publishing the correct version of the blockchain. In proof of stake we have an attack called the long-range attack. Now that's only true for naively implemented proof-of-stake blockchains that were the first iterations of this protocol, and it basically consists in going back to an early block and rewriting history, because there's no delay introduced by computational calculations as in proof-of-work. You can get blocks very quickly and just go back to maybe the Genesis block or a very old block and just recreate a long chain and trick the network into accepting this as the correct version. Now that's obviously not possible if you introduce the right type of penalties and stake slashing policies, but it is something that was possible in early versions of proof of stake. So another thing that can happen with proof of stake is that there's poor randomness. Proof of work really is not a consensus algorithm as such. It's a big random number generator, because you cannot predict who will be the next block producers. Proof of work is really a mechanism to make producing blocks expensive and random. So in proof of stake you have to rely on other ways of randomizing this process. Obviously you could just do it in a round-robin way, but then it doesn't always be possible to predict the next block producer. And randomness is generally very difficult to achieve in blockchains because of the nature, that they basically have to execute the same on every node, and in the distributed nature of this makes it a very deterministic system, and very hard to have the entropy required for true randomness. The Ethereum 2.3 research efforts have a big part just centering on randomness, and that's very interesting research. Now then, in delegated proof of stake, you can obviously get delegators to collude, and we can see that happening on EOS quite a lot actually. Delegator collusion just means they agree on certain things, like trying to maintain themselves as delegators and voting for each other, and they you know, that way they could also rewrite the blockchain, which is obviously a security risk. So just some incidents that have already happened. Now, 51% attacks we've seen quite a lot recently. The sort of most big one, the biggest of these were maybe the attack on Ethereum Classic, on Vertcoin and Bitcoin Gold, all happening about 6 months ago, if I remember correctly. And that actually the attacker managed to get away with some money through renting hash rate to rewrite a few blocks at a time, and perform a double spending attack. So that's obviously something we have to be aware of if we use smaller blockchains. And the increasing split and fragmentation in the blockchain community, talking here about sort of public proof of work blockchains that keep forking off of each other, that sort of increases the problem, because you then get a lot of small blockchains backed by a large number of backed by a very small number of nodes, and much less computing power. And the Verge attack is an example of a blockchain that had a big security incident because of trying to do too many things at the same time. It's just whenever you introduce too much complexity in a system, you also introduce a security risk, and I think that's a very good example of this. Now, Verge had 5 different mining algorithms, allowing different people to work in different ways, mine blocks in different ways, and they all each had their own difficulty. So that was already a reduction in security in a way, because the actual difficulty for a certain algorithm was much lower than the combined would have been. They also had very flexible timestamp policies, and difficulty adjustment based on how quickly the blocks are mined, which most blockchains have. But the combination of these three meant that an attacker could change the timestamp of every other block by an hour, so that blocks seemed to be generated very slowly, and that lowered the difficulty of one of the algorithms, making it much cheaper for this attacker to perform a 51% attack. So I find that a very interesting example of how trying to be too clever actually makes things worse. And yeah, that's an interesting incident. So then Lisk, which is a popular blockchain project working on a sort of a multi-sidechain solution, that they have a security issue where the actual addresses are 64-bit of a public key, but they actually not matched to a particular public key when addresses are initially created, or when funds are sent to an address. So the problem there was, and still is to some point, that if you send funds to an address and that address has not claimed this address with the corresponding public key, you can actually find any public key that ends with these 64 bits of the public address. And the difficulty of this is much lower than calculating a 256 key. it's actually 2 to the power of 64, which is doable with modern hardware. And you know, the amount of money that was at stake there actually made it worthwhile for people to do this. And I think Lisk is an example where people worked on a protocol without the essential background in cryptography. They didn't realize this, and they've taken some measures to advise people to claim their addresses immediately, but the problem is still there, and it's impossible to remove really without just redesigning the whole thing. So yeah, very important. If you do design blockchain at this level, you need a number of skills, and in your team you probably need some sort of distributed systems researcher and engineer, but you also need cryptographers, you need game theory expert, financial experts. So there's a number of multidisciplinary skills involved, and if you don't have all of these, you might end up with a security risk. Very important lesson as well, I think. Yeah, as always, I end this video with a call to get audited. Obviously, if you think you have a very clever blockchain protocol and you develop this, get it audited by a number of experts from different fields. And that's it for now. In upcoming videos, we'll dive into more technical details. So yeah, looking forward to that.